In this video, we're going to learn about direct variation and partial variation and how to identify the difference between each of them. In this first example, we're being told that Carly is driving to Montreal at 60 kilometers per hour. And we're being asked to fill in a table of values to show her distance as time goes on, up to 10 hours. And then once we have that table of values, we're going to graph the relationship and we're going to label the independent and dependent variable on the axes. So first we're going to fill in our table of values. So our independent variable is time in hours, and our dependent variable is distance in kilometers. So at time 0, she has gone 0 kilometers. After 1 hour, she's gone 60. After 2 hours, she's gone 120. After 3, she's gone 180. After 4 hours, she's gone 240. After 5 hours, she's gone 300 kilometers. After 6 hours, she's gone 360. After 7 hours, she's gone 420. After 8 hours, she's gone 480. After 9 hours, she's gone 540. And then if we went all the way to 10 hours, we ran out of boxes, but she's gone 600 kilometers. Okay, so now we're going to graph that information. So our y is our dependent variable, so that's the distance in kilometers. And then our independent variable is time in hours. So we are going to go up by 60 kilometers each time. So 60, that would be 120, 180, then 240, then 300, and so on. And then our time in hours is going to be just 1, 2, 3, 4, 5, 7, 9, and then that would be 11, and so on. So every line will be 1 hour. So now we're going to plot our information. So at 0, time 0, we've gone 0 kilometers. After 1 hour, she's gone 60. After 2 hours, she's gone 120. After 3, 180. After 4, she's gone 240. After 5, she's gone 300. After 6, she's gone 360. After 7, she's gone 420. After 8, she's gone 480. After 9, she's gone 540. And finally, after 10, she's gone 600. So if we had labeled that whole thing there. So we can see that it's going up in a linear fashion. I'm going to draw a line of best fit, like so. And there we go. So there are some questions to be considered. So the first question is this relationship linear or nonlinear? And it's linear because it's going up in a straight line. And where does it cross the y-axis? It crosses the y-axis at the origin, or 0, 0. And another thing it's asking us to do is to write an equation to find the distance she traveled after t hours. So if we were to write this as an equation, d equals 60t, because for every hour she's traveled, we will know she's gone 60 kilometers. So use the equation to determine how far she could travel in 15 hours. So what we're going to do is put in 15 for t. So d equals 60 times 15. That's equal to 900 kilometers. So one thing to note is that it's way easier to plug a value into the equation and it's much more efficient than to draw out a graph all the way up to 15 hours, because we would have had to keep plotting points or keep adding things into our table of values. So writing an equation and then plugging in the missing value is way easier. So the example that we've just worked through is an example of direct variation. Another way to say this is that one variable varies directly with the other. So in direct variation, you're going to have a linear relationship, and it's going to pass through the origin or through 0, 0. The next examples we're going to look at will be a little bit different. So direct variation occurs when the ratio of the variables does not change. So in other words, when the dependent variable is a constant multiple of the independent variable. So this is how we algebraically can represent direct variation. Y equals mx. So a few things to note here. M is the slope. And this is also known as the rate of change. And the other thing that we have to note with direct variation, that the graph passes through the origin, which is also known as 0, 0. So there's two key parts to direct variation. The graph has to go through the origin, and it has to go up by the same rate. Okay, so we're going to do a couple of examples where we will solve to find the slope or the rate of change, which is also represented by m. So the first one, the distance traveled by a car varies directly with time. The car travels 270 kilometers in 3 hours. So we need to find out what the rate of change is. So m is equal to the rise over the run, or the dependent variable over the independent variable, or y over x. So in this example, we've gone 270 kilometers in 3 hours. So that is equal to 90 kilometers per hour. So that's our first example. In another example, we're being told that the total cost varies directly with the number of games bought. 8 games cost $480. So this time, slope is going to equal $480 divided by 8. And that's going to equal $60 per game. So each game costs $60. So slope is another way of looking for the unit rate. So we practice those at the beginning of our course, calculating unit rate of change. This is the same thing. It's just called slope now. It's still the rate of change, or the unit rate. So in our next example, we're being told that Chris works part-time and he earns $7.50 an hour. So we're first being asked to describe the relationship between his pay and the hours he works. So we can say that his pay varies directly with the hours. For every hour, he earns $7.50. So if we were to write that into an equation, we would say, remember, we have to put it into the y equals mx format. So y equals 750x. So he's making $7.50 an hour. Another way you could put it, if we wanted to represent, so his P equals 750 and then times that by the hours, that would work too. So our next one, we want to find out if he makes $78.75 in a week, how many hours did he work? So we can plug in our information. So y equals 750x. We know that he made 78.75 equals 750x. We want to find out how many hours, so what x is. So we need to divide both sides by 750, and that will give us x. So these will cancel out over here. So we have 10.5 equals x. So that means that he worked 10.5 hours that week.